Let's look at coding some data. We're going to start off by looking at an example where the data is so simple there would be no need to code it, but it will be very good for giving us some understanding of the general rules that will help us understand how coding could work for much harder, more complex data. Okay, so this is our original data set, and let's say that we wanted to calculate the mean. We would say that the mean of this data is 11, 19, 29, 40. 40 divided by 5, we have a mean of 8. Okay, so we've calculated the mean of this data, and we know it has a mean of 8. Now we need to calculate the standard deviation, so we'll have a quick reminder of how to do that. We first have to calculate the variance, which is the sum of each of these squared, so sum of all of our data squared, in this case 16 plus 49 plus 64 plus 100 plus 121, divided by our number of data minus the mean squared. When we plug all of that in, we get 6. So our standard deviation is 6, square root of 6. Okay, so we've got that information. I'm just going to make a note of that over here. X bar is 8, mean is 8, variance is 6, and standard deviation is the square root of 6. Okay, so what is coding? Coding is where we add, subtract, multiply, divide all of our numbers by the same thing. So we apply the same formula to all of our numbers. We might do this if all of our numbers are extremely high or extremely low to make them more manageable numbers. Computers can work much better with stuff like this. If they're decimals which have a whole load of numbers which are the same at the beginning, such as, but then it's only this last number which varies, we wouldn't want to bother with all of that. We could subtract the 4.004227 and then times that answer by 10 to the 1, 2, 3, 4, 5, 6, in order that we just get a list of numbers such as this 8 here. It would be much, much better to work on that than a whole series of, we call these floating point numbers. Much quicker and possibly more accurate. Okay, so what code could we apply to this? We'll just look at some very simple ones for now. So we'll say that the new data y, we were using x before, is just going to be the x value minus 4. So we're just going to subtract 4 from each of these values, giving us a new list, 0, 3, 4, 7, and 6, and 11. 7. For some reason, subtracting 4 is the most difficult thing I've ever had to do. Okay, now we find the mean of these, so adding them all up, 3, 7, 14, 20. So y bar will be 20 divided by 5, it's 4. If we compare that to this, so let's just make a note of this in a different colour. It makes sense. We had a mean of 8. We subtracted 4 from all of our data, so we would expect the average to also reduce by 4. That's sensible. Okay, so what about our standard deviation and variance? So variance, exactly the same formula, and when we do that calculation, it comes out as 6 again. So we've got the same number. Is that sensible? Have we made a mistake? When we think this through, we remember that variance is a measure of how spread out our numbers are. We have taken all of our numbers and moved them all down 4. So they were here, we've shifted them. That hasn't actually made any of the spread smaller. They were spread out by, on average, the square root of 6. And in fact, when we find the standard deviation, we will find that that is still the square root of 6. Nothing will change there. So when we look at our, let's call it variance of y, that will still be 6. the standard deviation of y will still be the square root of 6. Because we've subtracted the same amount from every single number, they will not vary by any more or any less than they did before. Variance and standard deviation remain the same if all we've done is translate our data. We've subtracted or added the same amount to each piece of data. Okay, let's look at another code. So we'll now look at Z, and we'll say that for Z, we're going to double all of our data. So that gives the data 8, 14, 16, 20, and 22. We calculate the mean of this, so add them all up, and that's going to give us 80. 80 divided by 5 gives us a mean of 16. Again, I think that's expected. If we double all of our data, the average will also double. We're going to get a mean of 16. What happens to our variance? When we do the same calculation again, we actually get 24. So where has this number come from? That is actually 4 times the variance of x. Why 4? Well, again, let's think about what variance is measuring. It's measuring the spread, and we have doubled our data, so it has become twice as spread out. So why is this a 4? Remember that variance is working in units squared. So if I've doubled the distance between each of them, that means that the variance will be doubled twice. It will be 4 times greater. So variance will change by the square of whatever we've multiplied by. Standard deviation, as it's the square root of this, will now be 2 times the standard deviation of x. Doing that calculation, you will see it comes out as 2 root 6. Okay, so when our transformation is double, then our z bar will be double. Our variance of z will be 4 times, remember, because the spread has been doubled and variance works in units squared. And then finally the standard deviation of z will be 2 times the standard deviation of x. Because we've square rooted that, the spread has doubled, so the standard deviation should double. Thinking that through, it should make logical sense. Some of the problems you try in lessons will make it clearer why coding is usually a good idea if you've got very large or very, very detailed numbers which share a lot of the same first few significant figures.